Hi, today we're going to look at section 28.5, other trig forms. We're going to start by looking at a couple of identities, the first three of which we actually talked about in the last section. So those are the main trig identities, and we're also going to look at two others. So cosine squared and sine squared rewritten as forms of cosine of 2x. So those are going to be useful in a little bit. So we're going to need these 5 in order to make integration easier. So the first thing we're going to start off with is integration of things of the form sine to a power, cosine to a power, where at least one of the powers is odd. What we're going to do is we're going to use u substitution, with u being cosine of x if n, the power of sine, is odd, or u equals sine x if m, the power of cosine, is odd. If both of them are odd, you can do either one. So our first example is sine to the 4th cosine cubed. So since the power of cosine is odd, we're going to let u equal sine. So that gives us that du is cosine of x dx. So what we did here is I'm breaking up cosine cubed as cosine squared times cosine, so that we have the cosine x dx. And the next thing we're going to do is we're going to rewrite cosine squared as 1 minus sine squared. Okay, so that's from the first trig identity. And then we just start using the substitution. So sine to the 4th is u to the 4th, 1 minus sine squared is 1 minus u squared, and cosine x dx is du. Okay, so there's the u substitution. The next thing we're going to do is we're going to distribute the u to the 4th. So we get the integral of u to the 4th minus u to the 6th du. Integrate and replace back what u is. So we get a polynomial of sine x. And in order to double check it, you can differentiate it, and then you'd have to use a little bit of trig identities to get it back into the form that you started off with. But they are equal. So the next example is cosine squared sine. So since the power of sine is odd, it's 1, we're going to let u be cosine. And then we differentiate, and we get du equals negative sine x dx. And then if we do u substitution, we end up with the negative, and then the cosine squared becomes u squared, the sine x dx is the du, and again with the negative. Then we integrate, and then we replace back what u is. So if we have things of the form sine to a power, cosine to a power, and at least one of them is odd, then we just end up, after u substitution, with a nice polynomial. So the next question is, well, what if neither of them are odd? What if n and m are both even? So if that's the case, then we need to use these two identities. So the last two identities from that first page. So we'll see how that works. So for a nice easy example, we're going to start off with just sine squared x. So we replace what sine squared is according to the equation. So I'm going to pull out the 1/2, and then we're going to integrate 1 minus cosine 2x. Using the u substitution u equals 2x, we get the following. So the integral of 1 is x, the integral of cosine 2x is 1/2 sine 2x. And again, that 1/2 here is coming from the 2x over there. If we had something with, say, sine x and sine squared x and cosine squared x, we would replace both of them with the two equations, and we'll end up with a polynomial type thing with cosine of 2x. And then here I've just distributed the 1/2. So you get 1/2 x minus 1/4 sine 2x plus c, which is probably the form that it has in the back of the book. So the next thing we're going to talk about is powers, is integrals of the form secant to a power, tangent to a power. So what we're going to look for, because remembering that integration is the opposite of differentiation, we're going to look for things of the form secant squared x dx along with even powers of secant, or secant x tan x dx along with even powers of tan x. So for this first example, we have secant to the 5th x tan x. And we're going to pull out one of the secants and move it with the tan x to get secant to the 4th secant tan x dx. So we have one of the things that we were looking for. Note that the remaining power of tangent x, namely to the 0, is even. So we're going to let u equal secant x because du is then secant tangent dx, right? So they are the same. And then replacing, using substitution, we get the integral of u to the 4th du. Then we integrate, and then we replace back what u is. So we get this really nice 1/5 secant to the 5th x plus your favorite constant. And if you differentiate it, you will get exactly what we have in the integrand. As another example, we have secant to the 4th x tan x dx. And I'm going to separate the secant to the 4th as secant squared secant squared. So you have secant squared tangent secant squared x dx. And just like I said in the beginning, you have secant squared x dx, and you want the remaining power of secant to be even, which it is, it's squared. So then I'm going to replace secant squared with 1 plus tangent squared, again using those trig identities. And then the tangent's the same, the secant squared is the same. So the only thing I'm doing is replacing secant squared with 1 plus tangent squared. And then I'm going to let u equal tangent, because du is secant squared. So we get the same thing that we have there. So again, the whole idea of integration is to think backwards from differentiation. And then I start with my u substitution. 1 plus tangent squared is 1 plus u squared. Tangent is u. Secant squared x dx is du. Distribute the u. Integrate. Replace back what u is. So again, we end up with these different polynomials, either in the form of secant or in the form of tangent. The next one we're going to look at is tangent cubed x dx. So I can't pull out a secant squared, and I can't pull out a secant tangent because there's no secant. So if there is no secant, we're going to do the following. We're going to rewrite it. We're going to pull out a tangent x and make it tangent squared x tangent x dx. And then I'm going to replace what tangent squared is. And again, by the identities from that first page, tangent squared is secant squared minus 1. Then I distribute the tangent, and I'm going to split up the two integrals. So I've got tangent x secant squared x dx plus the integral of tangent x. And again, because we have secant squared x dx, I'm going to let u equal tangent x, so that du is secant squared x dx. So using u substitution on the first integral, we have tan x secant squared x dx becomes u du. And then the integral of tangent x we're leaving the same as the integral of tangent x. Integrate. Again, this integral of tan x being ln of absolute value of cosine x is from the last section. And we replace back what u is. Okay, so hopefully not too bad. If we have things like cosecant to a power times cotangent to a power, it's similar to what we just did with secant and tangent because the derivatives are very similar. So we'll do one example. So the integral of cosecant to the 4th x cotangent x dx. We're going to pull out one of the cosecants and make it cosecant cubed times cosecant cotangent. And we're going to let u equal cosecant, again, because du is now negative cosecant cotangent. So again, the idea is to get what we have. And then plugging in the u substitution, we get the negative integral of u cubed du we integrate, and then we plug back in what u is. So hopefully it's not too bad. You want to look for the derivatives that we already know. Things like secant tangent, cosecant cotangent, secant squared, cosecant squared. Okay, so just remember that integration is the opposite of differentiation, so use what you know from differentiation to help you with the integration. Okay, let me know if you have any questions. Send me an email, message through Canvas, whatever you want. Okay, have a nice night. Bye.